Now, on the simulation side, we take a separate approach. We first will apply a discrete event simulation of quantum networks framework. And here, we're using this event-driven logic for simulating quantum and classical processes in networks. So the main idea of this framework is that you have these physical components in a real network that are actually being modeled explicitly in our simulation. Simulated network events are scheduled for future times and triggered in chronological order. We actually don't need to simulate time in between the events. We can jump straight ahead to whatever event is next in the queue as is standard in discrete event simulation. Now, whenever a event occurs, we have these simulated components who are listening to particular events. If an event occurs that they listen to, they then have the option to perform some actions based on the event that occurs. Now, those actions can either be operating upon the local quantum or classical data that that device controls, or it can be used to schedule future events, which is how we iterate the time evolution of the system. So the way that this looks with a more practical example is on the left, we have some physical components. We have a photon source. It's emitting photons through an optical fiber, which then are detected. So on the right, we have sort of our discrete event simulation timeline that describes this process. Above, we have the source, optic fiber, and detector as our simulated components. And below, we have these green boxes which dictate the quantum processes and operations that are being applied. This timeline in the middle is our event queue and just schedules and processes all of the events that happen in chronological order. So at the start of the simulation, the source might trigger its emit process. So this means that it'll prepare the photonic quantum state that's going to emit. That might take up some time, so it'll schedule a future event for when that preparation is finished. When the preparation is finished, the source listens for that event and then emits it to the next component. Upon emission, an event is scheduled that the optical fiber listens to, which is I received a photon at my input. When the optical fiber receives that event, it knows to schedule a future event for when that photon exits. In the future, that event is processed and the photon exits the fiber. However, before it exits the fiber, we apply any of the noise necessary to model the transmission. We apply the loss and we apply the latency accrued. So the photon is emitted at a later time, and then finally it arrives at the detector. The detector receives this incoming photon event, which means it starts its measure process on that incoming photon. Once again, this measure process might take some time, and at the end of it, it's going to share back the result that was received, and that detector will put that result into a buffer to be analyzed later. Now, this process can repeat many times to collect lots of statistics, which then can be used to gain insights about how a system might actually behave in a real-world way, and allows you to look at the statistics and see the behaviors at a very granular and fine-tuned level.